Welcome to Unwired Learning. In this video, we're going to continue our series of AC circuit analysis videos, and this particular video is going to focus on doing a mesh current method problem. So here you can see I have another AC circuit, this time with both a voltage and current source, and again we have an inductor and capacitor in this circuit. So let's go ahead and think about this circuit for a second and ask ourselves, why would we choose the mesh current method over, say, another method like the node voltage method? And in looking at this circuit, you can see that I would have one node here, and then I would also have to have a second equation, a second node equation here, if I were to choose the node voltage method. But when it comes to the mesh current method, while at first it may seem, oh, I have a mesh here as well as a mesh here, I do have a current source in between those two meshes, and therefore the appropriate way to do this circuit would be to do a super mesh around the entire outer loop. And then I would have a constraint equation based on the current that is in between those two loops. So therefore, I actually think it would be slightly easier to do the mesh current method with this particular problem than it would be to do the node voltage method. Not only that, the problem is actually telling us, hey, use the mesh current method and express the result in polar form. Therefore, I guess we're going to do the mesh current method. So let's go ahead and label our meshes and our super mesh. On the left, we'll label that as mesh I1. On the right, as mesh I2. And of course, around the entire outer loop, we have our super mesh. Let's go ahead and write our super mesh equation, starting with our voltage source all the way on the left. And remember that when we're doing mesh current method, what we're actually doing is we're looking at the voltage drops across each one of the circuit elements. And since this is AC, we're going to look at the voltages across not only resistors, but also things like capacitors and inductors. And this problem has already helped us out and given us the impedances for each of those elements. In fact, again, as we're doing mesh current method, just like when we did node voltage method for AC analysis, we don't use resistances, we rather use impedances. So again, for our super mesh, that equation will turn out to be 24 angle 0 is equal to 2 times I1 minus J2 times I2 plus 2 times I2. Now all we have to do is let's isolate the terms that are specific to I1s and the terms that are specific to I2s. And in doing that, we get that this equals 2I1 plus I2 times 2 minus J2. Now we can't really do anything else to simplify this now. Instead, what we need to do is we need to look at our constraint. Here in the middle of the super mesh, we have a current that is pointing upwards, whose value is 2 angle 90. What we recognize is that since it's pointing upwards, that it will be I2 minus I1. So we can write that our constraint is I2 minus I1 equals 2 angle 90. On the polar graph, this particular 2 angle 90 would be pointing straight upwards, and it would be completely imaginary. See, at 90 degrees, that's the imaginary axis. So therefore, I don't even have to do any kind of conversions or anything, special math here. I can just know that this in rectangular coordinates will be 0 plus J2. Since we need to solve for the V out in this particular problem, it would be useful for us to find the mesh current I2. Therefore, I'm going to isolate I1 in our constraint equation. In doing so, I get that I1 equals I2 minus 0 plus J2. Now what I need to do is plug this equation from our constraint into our super mesh equation in order to get an equation that is solely based on I2. When I do that, I get 2 times the quantity of I2 minus 0 plus J2 plus I2 times the quantity of 2 minus J2. Now simplifying this and isolating our variable I2, I get that the right-hand side is I2 times the quantity of 4 minus J2 minus J4. Now what I can do is I can go ahead and add J4 to both sides of the equation and then divide by 4 minus J2 to isolate our I2. And what I get is I get I2 equals 24 plus J4 divided by 4 minus J2, which equals 4.4 plus J3.2. Since I2 is the current that will be going across the 2 ohm resistor at the output, all I have to do is a simple application of Ohm's law in order to find the voltage across that resistor. When I write out that equation for Ohm's law, I get that V out equals 4.4 plus J 3.2 quantity times 2 ohms. Multiplying out by 2, I get that that equals 8.8 plus J 6.4 volts, which in polar coordinates would be 10.88 angle 36 volts. So we can see that as before, we went from 24 volts with no reactance to a output voltage that is less because of the voltage divider that we have here, and we have a shift in the angle due to the inductor and capacitor components in this circuit. And as you can see also, that performing things like mesh and nodal analysis in AC circuits is really not significantly different than that of a DC circuit, with a couple of exceptions. Of course, the first exception is that we're going to take into account the impedances of elements like the inductors and capacitors in the circuit. And of course, we're working with AC signals. And when we do that, we have to look at the phase angle as well as the magnitude of those values. Now that we've found our voltage value, that concludes this video of Unwired Learning.